Yeah.
All right. Okay, so we today have our speaker, our new colleague at the University of Minnesota from the Department of Soil, Water, and Climate, Peter Neff. He's an assistant research professor in that department since August 2020. So probably under normal times, more people would have seen Peter around our department, but obviously there's reasons why that has not happened. So Peter has a couple of degrees from the University of Washington, and then his PhD is from Victoria University in Wellington, New Zealand. He then did a postdoc for a few years at the University of Rochester, that's the one in New York, and then back to the University of Washington for a postdoc, and then to here. He has many research interests, but a lot of them tend to focus on polar regions, Antarctic science. On his website, you'll see intriguing words and phrases about ice cores and geochemistry of dust in the southern oceans, and paleoclimate, as well as I think more recent climate. And so lots of interaction and intersection with the department here. So I was excited to invite him to come and give a talk to us. Peter is giving the talk from Tate Hall. He is in the building. And so I hope that afterwards, anyone who is also in or near Tate can meet Peter in person in a safe and distance, but friendly social mingling way outside, despite the somewhat cooler temperatures, which is appropriate, right? You're going to talk about polar things today, so that's great. So Peter, I'm looking forward to your talk.
Great. Thanks for that introduction, Donna. And yeah, I'm excited for anybody who can come around afterwards. It'd be great to chat. And my student, Julie Andreasen, is also here as well. And we're eager to meet more folks around campus. It has been an odd year. So I'll just share my screen here and we'll get going. Everything look good? Should I take the silence as a yes?
Looks great.
Great, thanks. And that's always strange in Zoom. I can't see anybody except for my slides here. So, well, thanks again for having me. And I'm really pleased to be here and pleased to be at the U, if over on the St. Paul campus. And I want to talk to you today about sort of my biggest research ambitions, which are to expand the array that we have of ice cores in West Antarctica to capture Pacific coastal climate. So moving us from higher elevation inland regions to the fast changing coastal sites. And a broader goal that goes along with that, and maybe an alternate title, is not only do I want to expand our climate observations through ice cores in West Antarctica, but also update the records that we have so that any new record we get, we have a fully updated array to compare that new record to. So I'll hopefully give you a good background of the features that we take advantage of at the coast where we could get ice cores, and where I am proposing to get more ice cores in the future. Learn about that coastal region and some of the major changes that are going on there in coastal West Antarctica. I did want to give credit to some interesting University of Minnesota history in Antarctica. So back in the very early days of the Antarctic program, after the International Geophysical Year, geologists from the department did a lot of work, and so their names are scattered across certainly the Ellsworth Mountains, Teal Mountains, and there was a lot of work done in the Jones Mountains, where you would find Pillsbury Tower, which I found a photo of for you, named after your former geology buildings. You can see that sharp peak there with the shadow. This is one of the few aerial photographs from mapping flight back in the 60s as well, I believe. It's a remnant volcanic cone, if you're interested in that. So one of the volcanically active mountain ranges there, the Jones Mountains. And it's actually 8,000 miles, almost exactly due south of Pillsbury Hall. Another big name from Minnesota that had a big impact in Antarctica was Robert Rutherford, who for his PhD mapped the entire Ellsworth Mountains, home of the highest peak in Antarctica, Vincent Massif. And he also grew up in the neighborhood that I live in, went to high school, where I walk by just about every day with my 2-year-old daughter. So some great local history. And his dad actually was the leader of the extension program on the St. Paul campus back in the 50s and 60s. another Minnesota geologist who answered a fundamental question in Antarctic geology shortly before he died in an aircraft crash in Antarctica. Edward Teal answered the question whether or not Antarctica was one continent or two, which we didn't have a good answer for until seismic traverses were made from the Ellsworth Mountains, where Rutherford mapped to near the South Pole, and it was determined that this lesser Antarctica that he's referring to in this short quote, which is West Antarctica as we call it now, was indeed connected to the rest of Antarctica. So although Antarctica is sort of a complicated complement with lower bedrock topography in West Antarctica, actually grounded below sea level, which is quite important for the future of West Antarctica, it was indeed one continent. There's not a seaway between the Ross Sea and the Weddell Sea. So some major contributions to Antarctic geology made by Minnesota geologists in the past, and hopefully more Antarctic work in our future. And I'll hopefully convince you that we've got some good work to do. And a simple way to talk about my interest in West Antarctica is just this fact that West Antarctica is more than just a flat white inland plateau. Coastal West Antarctica faces the Pacific Southern Ocean, and that's where we see much of the change in Antarctica. And so this is really what our West Antarctic glaciology community as a whole is addressing. And I'll talk a lot about that, but I want to take a minute to talk about something else that's really important in our broader geoscience research community. And similarly, sorry, I'm just acknowledging the scale of the place here as well, and how much we miss by not being out of the coast. But thinking more sort of backing up to the research community that we all occupy, I wanted to acknowledge that we started a conversation in the American Geophysical Union cryosphere community a week or so ago about diversity in geoscience, so geoscience, just like West Antarctica, is more than just flat white. Geoscience is more than just white males. So our fellows committee in our section, of which I'm the secretary, didn't forward any nominees to be considered to become AGU fellows this year because of a lack of any diversity. So the only criteria we had to judge this was data on the percentage of female nominees, which fell down. I think it was 6% of our nominees this year. So they decided to make a statement by not putting forward any nominations, which is the first time any section has done this, and certainly is fair for criticism. It's not necessarily fair to those who were nominated, but I thought I wanted to share a really great perspective from a young colleague, Melissa Diaz, which is a great analogy to Antarctica, which actually strangely connects to the way I'm thinking about how we think about Antarctica. So Melissa Diaz, who's a postdoc at Woods Hole right now and joining the faculty at CU Boulder in the next year, she had this sort of story to get across what we are missing in how we are putting fellows forward, at least in this AGU system. So if you design a sensor to install across Antarctica to measure snowdrift, and you design it for flat surfaces with negligible wind speeds, those conditions that you're most familiar with, you recognize there's a diversity of Antarctic landscapes, and it's important to fully sample that diversity. So you put your sensors in a range of conditions, and after a typical winter, you find that your data that you collected from flat, calm surfaces is great, but it failed in all of the other conditions. And so only having that data from that one type of environment, you go on to write a Nature paper saying that that particular flat, calm surface had the most snowdrift in Antarctica. And while it turns out the editor rejects your paper because you don't have enough data to prove your claims that those flat, calm areas were actually the snowiest in Antarctica. You can only compare calm, flat surfaces to other calm, flat surfaces. So that editor of the journal suggests that you reevaluate the efficiency of your sensor across diverse environments and strategize on how to improve it. And that's really where we are, at least with our award system at AGU. So we're not currently sampling the full diversity of folks in our research community. And so the AGU Cryosphere Fellows Committee decided not to move forward with a flawed system and to reevaluate where we are failing in that system and what we can do to move forward. So I wanted to take a minute to talk about that sort of front of mind here, because it's really needs to be a prominent topic of conversation across all that we do as scientists and as colleagues. So hopping back to Antarctica, I really appreciated Melissa's Antarctic themed analogy here for that broader conversation, and I'd be happy to talk about that more afterwards. But again, with my research, West Antarctica is more than just a flat white inland plateau. And so my simplest proposal is that we need to push ourselves to get out to the more complex coastal regions, which we're seeing change rapidly. And we have the opportunity to do that with some fantastic ice core sites that I'll go over with you. Again, this region is really large. So this is to scale the lower 48 over West Antarctica, and the Pacific coastlines of both of these are lined up and to scale. So both the west coast of the US and the coast of West Antarctica face marine moisture storms coming off the Pacific Ocean, the Pacific Southern Ocean in the case of West Antarctica. And that's where energy storms enter that system. And so another very simple way of saying this, I'll go over it later. I have another sort of version of thinking about that. So if we look here at this region of the coast, so basically the length of the West Coast, and you can fit California in our gap here where we have no ice core records, which are our only climate record in West Antarctica. If we put on here our map of the rate of ice thickness change from 2003 to 2019, we see that the areas across all of Antarctica that are rapidly losing mass are almost all focused along the Pacific coast of the West Antarctic ice sheet. Their ice shelves are thinning, and we very clearly identified that this is an ocean-driven process. Relatively warm, deep water is getting underneath floating ice shelves where the glaciers go afloat, calve off icebergs, but they're also thinning from below due to excess heat being brought in through coastal upwelling, which is a wind-driven process that pulls deep water under the ice shelves in these particular regions where there is bathymetry on the Antarctic continental slope that is deep enough to allow that warm water to get up underneath the ice shelves. And so the fundamental question in our research community, West Antarctic glaciology, is how much sea level rise will this bring, how fast? And this remains one of the larger uncertainties in projecting sea level rise to the end of the century and in the next several centuries. And that's because of, we often boil it down to a single glacier, Thwaites Glacier, pointed to right there in the center of the image. It's a glacier basin that holds up, it's 1 to 3 meters of sea level rise equivalent ice that could rapidly run away and retreat if we're unlucky and we're trying to understand how rapidly that ice will retreat and contribute to sea level rise. And so there's a lot of different aspects of geoscience that go into that. And so mine is to get us out there from where we've been at the top right here with inland ice cores in central West Antarctica, which have taught us a lot. No disrespect to, they have a lot of work that a lot of colleagues have done, and these records are where I started my career as well. But all of the thinning and the processes that are driving thinning are out there on the coast. And we have these coastal ice rises or coastal domes, I sort of refer to them interchangeably, that are fantastic ice core sites right on the coast. Another way to think about this is to bring it back to the lower 48 US states. If we care about weather and climate processes that are going on in San Francisco, are we okay with only having observations in Reno? And that's the arrangement basically to scale that we have with our current long-term meteorological observations in West Antarctica. So I'll put this on to scale. Traversing from Thwaites Glacier inland across the West Antarctic ice sheet divide, which is a deep ice core site, onto Byrd Station, which is our only long meteorological station in Antarctica that's been occupied since 1957. And so currently with ground-based observations, that's the one observational station, except for augmented by the array of ice cores, where we can ask questions about what's going on at Thwaites Glacier right there at the ice-ocean atmosphere interface. And so I don't think this is sufficient to really understand what's going on at the coast. So if we zoom back into the processes that are going on there at the coast that we need to understand in order to know how West Antarctica is going to behave in a warming world, we have complex interactions of not only ice, ocean, and atmosphere, but also the solid earth. So as ice is retreating faster and faster, they're unloading the solid earth below, and you have the responses there you have to account for in order to project how fast that system is going to respond. I've highlighted here in red boxes the processes that ice cores, in particular the coastal ice cores, can most directly inform us on. So there are global factors that are pushing around places like Thwaites Glacier. So we have strengthening westerly winds, which is related to global warming. We have teleconnections, these waves that are sent down in the atmosphere from variability in the tropical Pacific Ocean. We have to keep track of snow accumulation, which is our fundamental input to these outlet systems and to the Antarctic ice sheet in general. As we warm the atmosphere, It increases the amount of snowfall that we expect. There's that thermodynamic response to warming. And that warming can also change the atmospheric circulation. So there's a dynamic response to a warmer atmosphere as well as the pressure systems rearrange in response to different pressure temperature gradients. And so all of these processes have to come together to understand this system. And we have this broader climatological feature, the Amundsen sea low there at the bottom, that is the primary feature that controls the sort of weather system, synoptic scale storms that affect coastal West Antarctica. And so ice cores can inform these three boxes I've highlighted red, and they're important to give us not only a snapshot of what's going on at a system like the Thwaites Glacier or the West Antarctic coast in general, they give us long time series, 100, 200, several hundred year long time series of characteristic variability, trends, and extreme events that are affecting these critical outlet glacier systems. And so our general problem in Antarctica classically is that our observations of anything, but in this case of West Antarctic ice ocean atmosphere change, are fundamentally limited in time and space. So this sort of shows the combination of climate data we have from the West Antarctic ice core array, the bottom plot of the water stable isotope delta 18O anomaly, which is basically our temperature proxy. So this is just 100 years. Oops, sorry, I classically have the zoom controls over where my plot is, but because yes, I just misspoke because it's 200 years from the ice core array there. And then our instrumental weather stations only began with the International Geophysical Year in 1957. So moving forward, we have a temperature record, but to properly contextualize, say, the warming trend that we see in that upper part of the plot, the weather stations at bird stations show warming since the International Geophysical Year. But putting that in context with the past gives us a sense of how anomalous that might be. And then the only other observations we have to use in Antarctica are what we call climate reanalysis data sets. So these are our best observations incorporated into a climate model, assimilated into a climate model to have a globally coherent data set of weather and climate beginning in the satellite era. So in Antarctica, those are only reliable from 1979. And then we have our observations of how the ice is changing, thinning, flowing faster, only beginning in the 1990s. So that was a really short time scales to have perspective on such large ice systems that respond to multi-decadal and centennial forcings and beyond. And so the ice cores really give us much longer perspective on all of that. Another way of looking at this classic Antarctic problem is if we just put up a sketch of time on the x-axis and space. So our observations that we have are these station weather observations that begin in around 1960. We have scattered automatic weather stations beginning in the late 70s, early 80s. These are sort of patchy records, but scattered all over the continent. We thankfully have full satellite coverage beginning in 1979 that's now spatially coherent. And there's a bit of work you have to do to make sure that you ground truth those satellite observations. And importantly, with ice cores, we can go to any location across the continent, speaking broadly, and drill an ice core and go back in time from the present day beyond any of those observations we have, several hundred years, or if we really commit ourselves to it, thousands of years. And that is really important because then we, from those ice core records, have long records of climate variability or characteristic variability, which is quite noisy in Antarctica. You can document ongoing or emerging trends, and you can put extreme events into context. And so we have learned a lot from the ice core array that we have. We have very good spatial coverage of ice cores in West Antarctica compared to other regions in Antarctica. And that's largely due to the International Trans-Antarctic Scientific Expeditions of traverses in from 1999 to 2002. And they allow us to, for instance, put a relatively warm decade of the 1990s in context with the past. So it was a really warm decade, but it turns out not unprecedented in the last 2,000 years. That's from a paper that I was on 2013. For reference, the first science research I ever did was to run water stable isotope samples for these ice cores from the ITAS traverses. So it's great to think back to these data. And another important result from these was that warmth in the 1940s from a strong El Nino event forced a warm anomaly in offshore of West Antarctica and in the ice core array. And that may have played a role in the onset of retreat at Pine Island Glacier and Thwaites Glacier that's now likely to be in a geometry of unstable continued retreat. These cores also help us to confirm the accuracy of, or test the accuracy of climate reanalysis data sets, these assimilations of observations that tend to struggle in Antarctica because we have so few observations. So ice cores are the only way that we can get records of snowfall. We call it surface mass balance, the primary input to the Antarctic ice sheet system. It's only observable from ice cores. So you can't exactly measure snow falling in Antarctica. It sort of blows around a little bit. And in connecting this ice core array, the records of surface mass balance with the reanalysis framework, we're able to see there's a strong opposing trend in snowfall across West Antarctica, and there's also a background increase in snowfall that's likely connected to the background warming experienced across the Southern Hemisphere and the globe, of course. So this is showing that. So this is from 1957 to 2000. It's assimilating spatially the where they're on ice cores. It's using a reanalysis framework to extend relationships. And this shows a strong increase in accumulation in what we call Eastern West Antarctica. It's sort of the top part of the plot there. And the reds are a decrease in accumulation in Western West Antarctica. The directions down there are completely non-intuitive. But so this is a really important spatial gradient to understand. You can obviously see it's really a different pattern than the strong thinning or retreat that we see along the coast. So it plays a role in that. We have to make sure we capture that properly in our satellite observations of ice thinning. But also, if you look at the coastline there, we have no, the gray circles are ice core records. We have no ice core records to confirm the coastal trends, which tend to be the strongest trends in this study. So again, why we need to be out on the coast monitoring these things. And so for the rest of the talk, I'll mostly focus on my thoughts around how we can expand to coastal ice core sites. So I'll go over what these structures are, the coastal ice rises that are perfect ice core sites, what we're starting to do using NASA airborne radar. We have one shallow fern core from out there that gives us a sense of what the records are going to look like. And I'm working the next month or two to propose our first ice core site to get out to hopefully in the next couple of years. And then I'll briefly talk about how we can easily update the existing ice cores before wrapping up. So my sort of silly admission about ice core scientists is that we like ice domes. This is a classic diagram of the Greenland ice sheet, but it can be any ice sheet. We like to drill ice cores right at the ice divide where the flow situation is the simplest. Your ice is accumulating in a perfect stack. It's being advected only straight downwards. It's being stretched as it gets deeper, and you have that exponential increase in age of your stratigraphy with depth. And so that's why we tend to like to drill right at ice divides. We don't have to account for our ice at our ice core site having flowed in from upstreams, from complex correction involved with that. And so that's why all of our red dots across that map of Antarctica are scattered around the top there. This is where the situation is the simplest, the temperatures are the lowest, snowfall is lower, which is for deep ice cores tends to be a little bit more advantageous to pack more time in your stack of ice. And that's great, and we've learned a lot from it. Our proxies tend to be similar, distilled out to the middle of the ice sheet. Everything's a little more complex at the coast, and that's why it hasn't been the biggest subject of research. It's also the West Antarctic, the coast of West Antarctica is one of the most remote parts of Antarctica with the worst weather. So that also does have something to do with it, to be fully transparent. But thankfully in West Antarctica, we have these mini ice sheets, these coastal ice domes or ice rises that line the coast. And we haven't been to a lot of them on the ground, but we know a fair bit from satellite observations and airborne radar campaigns. And also from visual images. So there's this great archive actually hosted by the Polar Geospatial Center here on campus, or on my campus, the St. Paul campus. I've enjoyed working with Jonathan Punsack this summer on a conference, but I love these old aerial photos of the mapping flights from the 40s to the 70s that mapped the entire coastline of Antarctica. And this really gives you a sense of what it looks like to fly from inland West Antarctica. This is, you're looking at Mount Takahe is a volcano out there, and it'll fly over the Tony Mountains out to the coast. And everything's a little bit more subtle when it's on full Antarctic scale and there's no vertical exaggeration. But what you're looking at here is a place called Martin Peninsula, which is one of these coastal ice rises that's maybe 2 or 3 ice shelves down from Thwaites Glacier. And that's the Amundsen Sea out there at the left. And so we would, this ice rise is about 500 meters tall, so elevated above the really warm temperatures right at sea level, and has everything we want to see in an ice core site. And I'll go over this a bit more. So I wrote a little paper about some of these ice rises last summer, I guess. And so that flight that you just saw is marked with the red line on both of these plots. And in the bottom plot, the inset there shows a flight across the Getz ice shelf and a number of these ice rises, and shows their elevation and the bed elevation measured by radar instruments on NASA Operation Icebridge flights. And so you can see these nice little domes, ice rises, that are these perfect little miniature ice sheets out there right on beachfront property. If we care about what's going on in the Amundsen Sea, because it's driving warm water under Thwaites Glacier and these other ice shelves, Getz ice shelf is changing quite a lot itself. We have perfect ice core sites to observe the last several centuries of climate conditions, temperature, winds, snowfall that has been, all of those are inputs to the current state of those systems. So just to show you here, a classical ice rise that we've done a lot of work at, the Royal We going way back to the 1960s, is Roosevelt Island. So this is a view from above. This is a DEM, not a visual image, but you can see the structure, tens of kilometers in width and length here. And if we take a slice across this, having driven across the ice divide with a radar instrument, this is what the internal structure of these ice rises looks like. And this is why they're these perfect sites for ice cores. So a perfect stack of well-behaved stratigraphy. It's got this really cool feature right beneath the ice divide, because the flow regime is so simple right there. The particular stress regime underneath an ice divide makes the ice actually slightly stiffer. And so it arches up like this. We call them Raymond arches, after one of our professors at University of Washington, who came up with this stuff out of pure physics before it was ever observed in the field. And so we tend to like to drill on these things. And indeed, when I was a PhD student in New Zealand, we drilled to bedrock at Roosevelt Island, produced an 80,000 year long climate record of all sorts of great information that gives us a full regional picture of how a region like the Ross Sea has changed from the last glacial period. And I go to this as well to sort of show you what these, I'm talking a lot about hypothetical records, but I want to show you the sort of chemical proxies that we get from them. So this is annual layering at about 14 to 20 meters depth at Roosevelt Island. And so from the top there, blue is Delta 18O, our water stable isotopes proxy for temperature. So it's a good indication for seasonality. The next two or three plots in purple and orange are sulfur compounds measured on ion chromatograph and on ICP-MS. Those are really good proxies for sea ice, ocean conditions. If the surface ocean is thawed in the summer, you have a lot more sulfur emissions coming from the surface ocean. Skipping down to the light blue there is iodine, another good proxy for sea ice processes. Liquid conductivity in the melt stream of how we sampled this ice, and calcium and black carbon records of dust and biomass burning in the southern hemisphere. So ice cores are these really unique, high fidelity proxy records that can tell us a lot of information, especially if you're focused more in the last couple of decades to centuries at the coast here. Okay, so sort of reiterating some of the things that I've gone over. So we have this really big blind spot in the West Antarctic ice core array. It's the sides of California or the west coast of the US. And we're not sampling those low elevation regions where ice ocean and atmosphere are interacting and change is happening in West Antarctica. And we have a range of ice rises to choose from. We know we can't go to all of them. They're quite hard to get to. But we can start to study these before we are able to get out to the field and learn what we can. And that's what I'm up to right now with my PhD student, Julia Andreasen, as we also think to future field projects. So to start showing you some of these places that we're thinking about, here's one, Martin Peninsula, that you saw in that old aerial photography movie. And so this is each box there is 5 kilometers wide. So these features are sort of 15 to 20 kilometers wide. And you can see the internal stratigraphy there. There's just beautiful layering with thin layers on the east side because of, on the right side there because it's the lee side of the ice rise. And on the left is the high accumulation side. So you see those layers plunging slightly deeper. And that's the side that storms hit this ice rise. The closest I've ever gotten to any of these is on some of these NASA Operation Icebridge flights. I was lucky enough to have gone to 2 flights over Thwaites and Pine Island Glacier back in 2016. And this is one of the nearby ice rises just next door to Martin Peninsula there. And I show you this in part because it's I find it important to always sort of see with your own eyes, if you should be so lucky, these objects of study. But then, of course, one of the primary data sets that we have to explore these without going there on the ground is from these NASA Operation Icebridge flights. So on board these flights, which were undertaken from 2009 to 2019 in the period between the launch or between the end of the ICESat mission and the launch of the ICESat-2 satellite mission, NASA flew extensive missions all over Greenland and Antarctica and managed to fly from Punta Arenas all the way around the coastline of West Antarctica across just about all of these ice rises. So it allows us, using a high frequency radar they had on board, to build snowfall records that we can compare to climate reanalysis data. And if we have a flight that passed over an ice core site, we can compare also to ice core sites. So this gives us a chance to look at time series of coastal snowfall spanning recent decades, even though we can't get out to these sites on the ground. And so I'm showing now the work Julia has done in recent weeks. So we're still developing the method at simple inland sites. So this is showing a site called ITAS 2001-01-3. It's marked there by the larger inland dot there. And this is one of the sites where we have co-located airborne radar, ice core, and of course the climate reanalysis data set that we like to use ice cores and radar to validate. And so Julia's method so far, and she's had some great help from Andy Wickert's student Max, which I know she's appreciative of. What she's doing is taking 3 vertical transects through these layers. So this radar echogram is the bright returns there are reflecting off of annual chemical changes in the ice. And so Julia takes 3 vertical transects through these. You can think of them like 3 ice cores. And what you get from that is the peaks in the return power from the radar signal. And each of those peaks is the bright spot in an annual layer. And so you can pick those and plot them again on the same echogram. And sorry, the yellow dots are very tiny that mark those, but that allows us, if we know that you flew over in 2016, that the first layer that's buried there is 2015, and you can count your years below, and you end up with the time series of layer thickness. And I believe I counted the number of years wrong, but you know, we have cut this off at the year 1979 because we don't trust our reanalysis data before that. We need to do a bit more work before showing it. But if we can compare the radar snow accumulation just from counting annual layers, measuring their thickness from the Icebridge echograms, and compare that with the reanalysis, so it's from the ERA 5 reanalysis, total precipitation, you can see the correlation is quite good. And this is even despite not having made any corrections to the Icebridge data for the change in density, the densification of snow at depth. So to have a correlation R of 0.62, highly significant, is great. This is sort of still back of the envelope. And so as the method is firmed up, the plan for Julia with NASA funding for the rest of her PhD is to take these out to the other red circles there on the coast and see if she can build accumulation records from these coastal sites, which we've never had those records for. It's sure to be a tough job, but it'd be really interesting to see what we can learn. And the last step in all of this, of course, is to compare back to an ice core. And we're still having a little bit of difficulty with this ice core. The correlations are not great before 1990 for some reason, and we're looking into the data sets if we have something wrong there. But this is the ultimate test where you have all 3 of observations of snow accumulation in one spot to validate the radar method and also validate the accuracy of the modeled ERA 5 reanalysis precipitation. Another step that we're taking before going out to new sites is thankfully collaborating with colleagues at the British Antarctic Survey to look at one of the only very short ice cores we have from a place called Mount Sipel. It's a volcano right out there on the Amundsen Sea. And preliminary dating that we're still working through shows that we have good layering, annual layers from 1998 to 2016. So this is also giving us a good sense of the marine salt loadings, the basics that we should expect at any of these coastal sites. And it'll give us a first sense of broader regional correlations between snowfall records or the temperature proxies at this site and things like the Amundsen sea low, the pressure system that controls storm tracks in the region. And finally, the ultimate next step is to expand to a new coastal site. So I'm working on finalizing a proposal right now with colleagues at University of Washington, Dartmouth, and Columbia University to go collect 150-meter deep ice core. It's something we can do relatively fast, and that's a key emphasis of this type of field work. We're trying to go to a remote place and bring back a relatively large amount of ice. 150 meters of ice is on the order of 2,000 pounds with the way we drill it. And so we have to balance picking a site that's logistically supportable. So in this case, this is a place called Guest Peninsula that's logistically supportable from McMurdo Station, our main logistics hub. And it will, in that relatively shallow amount of ice, 150 meters is not that deep for an ice core. That will still give us 400 years of seasonal proxy records of all sorts of climate and environmental parameters. And so in submitting a proposal this year, and maybe there'll be a chance for resubmission if necessary, that would put us at being in the field by the 2023-24 Antarctic season. So that's the plans for expanding the array. And I know I don't want to talk too much longer and have time for questions here. But the important thing as well as collecting new ice cores is to keep our current array updated. So it's currently 20 years out of date. Most of it was drilled before 2000, 2001 or so. And this record has, again, been really valuable. So we were able to demonstrate in this paper that the 1990s warm water table isotope values were probably more elevated than the 1830s or the 1940s, but we actually weren't able to most confidently say that because the number of records that we had to evaluate this drops off in that bottom plot right in the 1990s and 2000s. And so that's a key shortcoming that we want to address. It already was a problem back in the early 2010s, and it's getting only to be a bigger problem as the ice core record is now 20 years out of date. So if we collect a new core, that's great, but the most recent 20 years of any coastal ice core, we won't have an array to compare it to. We won't have that spatial comparison to make to other ice core records. And this is a problem that's true all around Antarctica. It's really, I guess, difficult to justify going back to an ice core site even a decade or 2 decades later, because it's sort of just, that hard work of maintaining observational networks. It's not some shiny new thing. So some of the background work that you need to do to maintain observational networks. And thankfully in West Antarctica, besides getting there, it's relatively easy to do. And so I'll go back to that site that Julia is working on right now, ITAS 2001-3, to show you how easy it is to update these. So we know from the ice core record the accumulation rate really well. So it snows about 32, 33 centimeters per year. We haven't been back there for 18 years now. So that makes 5.85 meters of burial of that surface that was drilled back in 2001, plus or minus a little bit for some compaction and things. And so in order to overlap, double that depth and overlap with 18 years of the previous record. So a new core that we would drill that's 12 meters long would date from 1983 to 2020. A 12-meter fern core is something you can do with a little T-bar hand auger. So long as you can get out there, and there's a lot of logistics that's being supported out of a central hub in West Antarctica called Waste Divide. There are a lot of aircraft that are constantly waiting for weather there. And so the concept here would be take a small, 2-person team and fly out to any station or any ice core site where the weather's fine while you're waiting to get to some primary objective, and quickly collect a core. And sometimes it might take 5-6 hours to struggle your way down 12 meters, but it's relatively easy to do. And so in combination with these things, I've very ambitiously put a timeline. I've hesitated to do this in the past, but I wanted to give a sense of the amount of time that this would take, and this is still very, very a naive timeline. But so we're currently funded through Julia's success with the NASA Future Investigators Program. She won a Finest Award earlier this year, so congrats to Julia. Our next step is to propose ice coring at that #1 site there, Guest Peninsula, and the earliest that could happen would be the 2023-24 season. And if we kept some momentum going, this is a bit silly, to then bounce to updating the waste cores so that we can keep that spatial comparison with any new core. We're talking 24, 25 there. And then to pick a few of these sites along that coast where we see strong gradients and snow accumulation trends, having 3 or 4 other sites and pushing out there to that site number 4, Thurston Island, which could be sort of mid-decade might get to this. That's getting to be in territory where the British Antarctic Survey has logistical strengths. And I have pretty strong collaborations with colleague Elizabeth Thomas at BASS. So, a lot of this is theoretical, but the first steps are getting underway here with this proposal going in soon. And I think this is a great way to keep our observations most up to date, most useful in West Antarctica. These sort of results really filter into much broader communities than just the ice core paleoclimate community. The folks using the ICESat-2 laser altimeter system, they need really good constraints on snowfall to make sure their laser altimeter is actually giving them real information about ice surface height. Ice sheet modelers, folks who are calculating ice flow velocity, they need to have confidence that all of the surface mass balance, all of the snowfall records that they use in their models are actually as realistic as possible. And currently they have no constraints from that coastline. So hopefully we could have an expanded, updated WAIS ice core array by 2030. And then in going to any of these places, you can also get information that gives a sense of whether deeper ice coring, which would take a year or 2 at a site, is worth the effort. So I'll stop there. I hope I gave you some sense of what I'm hoping to do with new ice cores from coastal ice rises that would expand the utility of a well-maintained 200-year-long West Antarctic ice core array. So we've been at these high, dry, flat inland sites that we need to keep updated, but we need to push ourselves to get out to the more complicated coast where all of the ice-ocean atmosphere interactions are happening and all of the change in West Antarctica is focused. So thanks very much.
Thank you, Peter. So our tradition is that students get to ask the first questions. And while they're thinking about that, they're marshaling their awesome questions. I just want to say I really enjoyed your Minnesota and Antarctica intro. And have you seen the map that the PGC produced with every Minnesota place name? It's pretty amazing. It was produced at the request of Bob Rutherford. So.
Okay. Yeah, I was the funniest thing about that in it was part of my personal onboarding is checking this stuff. And actually I have Rutherford's PhD thesis in my office. So if anybody needs it, it's in my office, and I'll give it back only if you request it. But that video footage I found of his is actually from a Birkenstock advertisement that he did late in his life. And it's this fantastic 6 or something minute long video of him going through everything that he did in Antarctica. And it sort of has a surprise ending that it's a Birkenstock ad.
That's really funny. Okay, let's hear some student questions. You can either just unmute yourself and ask away, or
just 1 minute, please. But just I almost turn off everything here.
If you have a question, go ask. Yes, ask it.
Okay, wait.
Hello? Oh, I think a bunch of people are upstairs, right?
Right.
Okay.
Getting some of the
I was gonna
technical
mute.
logistics.
Yeah.
Okay, I think I'm good. Okay, if anyone wants to ask.
Or not.
Or not. Okay. There's a question in the chat, Peter, which I can read, or if maybe you see it.
Yeah, I can see them. So yeah, the first one I see is from Claude. So our methane hydrate deposits supply to what's currently known about Antarctic ice. I mean, if you're thinking of methane hydrate deposits offshore, I don't know much about that. I've done a little bit of work thinking about the way that gases in the ice are turned into clathrates deeper in the ice sheet. It actually causes some difficulty for us with deep ice coring. About 500 meters depth, the air bubbles in ice become so pressurized that when you take an ice core out of the ice sheet, it blows up, which is quite disappointing, I can tell you, as an ice core scientist to have. So we have this zone of ice where it's transitioning into clathrates that is quite tricky, but that might not be what you're talking about. And so from Wyatt here, for initial ice cores on the coast, you're hoping to get a few hundred years of data. Is that constrained to just time, or is it the max depth at those areas? So so the considerations at sites like this are really affected by how strict the logistical limitations are. So the deepest we can go with a quick field setup and a dry mechanical ice core drill is by about 200 meters. The ice becomes pressurized enough that it starts to fracture due to the cutting forces of the ice. So you already sort of can't go below 200 meters without really struggling. And with the snow accumulation rates at the sites, getting a couple hundred years for what I'm interested in, which is sort of getting background climate variables that play into the fundamental noise that you would go, start a regional ice sheet model with, right? If you're modeling Thwaites Glacier, you need to have a couple hundred years of regional winds and temperatures to spin up your model. And currently that's done with synthetic data. So a couple hundred years is good. It also captures quite a few cycles of Pacific Ocean variability, El Nino, La Nina, longer multi-decadal variability.
Hey, Peter.
Oh, you got a delay in your audio.
Oh, sorry. Anyway, I guess my question is, with such like broad ice sheets and a limited number of coring, how do you pick like a location that you sample when you're out there?
Well, you pick it well before you're out there, I guess. But in the past, I guess, so thinking of the ITAS traverse, which is where a lot of our West Antarctic ice cores come from, it's really restricted to where you can safely operate in the logistical modality that they were in. So they were driving tractor traverses that were put in by aircraft at one of the inland stations, and then they can drive anywhere where they don't have to cross the grounding line of the ice sheet, where the ice goes afloat and rapidly accelerates, and there's all sorts of crevasses. So that is one determinant. And then you tend to want to stick to ice divides, right at the top of your ice. I guess, it's like a hydrologic divide, but it's the simplest ice flow situation. Because if you drill on the side of an ice dome, where you drill, the ice didn't actually fall there when you get deeper. The steeper ice actually accumulated somewhere upstream, which is just a mess. So there's a lot of considerations: temperature, accumulation rate. On the coast, we tend to have really high accumulation rates, which is a bummer if you want to drill deep and have a lot of time in your ice core. But if you only need a couple hundred years and you end up with really thick years, like half a meter per year, that's really great for the sort of geochemical analyses we do. It's really easy to get a lot of samples.
Peter, this is Jonathan Punzek. I'm so happy to see that you're giving a talk for the department. So whoever lined this up, thank you very much. Although you're at a different department, it's so great to have you at the University of Minnesota, and we've had the good fortune of working together on the workshop you mentioned before. I just wanted to, if other people in this group are not aware of that, I just wanted to applaud you for your leadership on that. The final report is housed on the PGC website, but this workshop was looking at the potential of bringing a subsea cable, fiber optic to Antarctica for internet connectivity. So Peter just did a phenomenal job of organizing a very disparate but enthusiastic research community. So a few people could have pulled it off as well as you did, Peter. So I just wanted to applaud and congratulate you on that. And I'm really excited about just the potential, not only for interactions with PGC, but more broadly with the department and the university. So I think you bring so many positive positive things to the university. A question that I have, so when you're talking, this is fascinating because this is the first time that I've got to go in more depth to see some of the research activities that you have done and what you have planned. Obviously, you're one among many researchers that have been impacted, and there are far fewer people going to the ice right now, and hopefully that opens up before too long. If you're funded on more of these activities, do you have a sense of just what are you hearing, and as far as when groups are going to be more likely to go, and how is that impacting just your current kind of outlook and plans? And obviously you have such a strong field component to that, so I'm curious to know how you're navigating that. I know that impacts several other researchers in the department focusing on entirely different things.
Yeah. Well, thanks, Jonathan. Thanks for that about the workshop. It was a wild short time frame for a workshop. But yeah, it's a tough time in Antarctica right now. So I mean, we're being actively discouraged by NSF to submit new fieldwork proposals, which is a bit tough because many folks are just continuing to submit them anyway. So you sort of just have to stay in line. Folks who have been funded 2, 3, 4 years ago are having their field campaigns still canceled due to housing shortages at other international field stations because there are extra needs around quarantine. So yeah, it's good. I'm trying to have a balanced platform where we're focusing right now on airborne data from NASA IceBridge, just like an endless wealth of information. So that's really helpful. And yeah, it's just a tricky time to have been. I've been working more than a decade on these sort of projects, slowly sort of learning, right, sort of with each degree, having more responsibility on projects, and now 10 or so years later, I'm in the position to lead them. And just at that moment, we're being told, don't propose projects like this. So yeah, I don't know, it's a combination of remaining naively hopeful and also just really working and trying to understand the logistical constraints as much as possible. So it's really great right now. There's a big 25 million, 5+ year long project now at Thwaites Glacier to really understand that critical system. And so the logistical chain going out there is really, really strapped. So, I would love to go to ice rises that are right out there. You can't do it. And so we have to be a little bit more tricky. So that's why I've sort of shifted to this first site I'm proposing, which is more or less supportable directly from McMurdo. And that, yeah, it's tricky, because you tend to, when you send a proposal to the National Science Foundation, you should not compromise the science around logistics. But in Antarctica, it really, if you're not living in the reality of the situation down there, it's you can be just wasting your time. So yeah, it's tricky, but got to keep trying.
Yeah. Thank you.
There's a question in the chat from Hema, Peter.
Yeah, so based on the thinning map, there's a lot of mass loss across the coastal regions. There are any differences in mass loss between the coastal coring sites that you're expecting, maybe based on ocean temperature variability, topography, weather patterns? Yeah, and the really cool thing about those thinning maps is that they highlight a lot of different processes all at once. So in the regions of broad thinning, if you looked at any of these ice rises that I'm talking about, going back with all of the wealth of knowledge you now have about Antarctic ice rises, you'd see actually that there's very little thinning at the ice rises themselves because they're relatively disconnected from the ocean, right? They're not extending a tongue of ice or an ice shelf of ice out into the ocean. And so you'd see a lot of little blue or neutral dots out there right in the middle of the deep red thinning outlet glaciers. And that's one of the coolest confirmations that like it really is the ocean that's driving things. If you can have within the space of 5 kilometers a fast flowing outlet glacier that's thinning rapidly, and then this perfectly happy little ice rise, that they're disconnected from the process that's driving the thinning at that other place. So they're certainly then still proximal to the ocean forces that are driving the ice sheet thinning. So there certainly are going to be differences in what those sites experience relative to the interior. And that's like the simplest part of my argument is like, if your job is to understand why a building is burning, you're not going to just watch from like across town and be like, oh, I wonder what's going on. Like you sort of need to go there and really figure it out. So it's like the simplest argument is just proximity. We have sites where we can better understand the climate that's affecting the coast of Antarctica, and it's just that they're hard to get to, and that I'm the only person who's silly enough to push to try to get there.
Other questions from anybody? Larry's hand is raised. Go ahead, Larry.
Let me see if I can make myself visible and then
Mhm.
that you can hear me.
Gotcha.
So that was I mean, it's a really interesting talk. I could pick your brain for a long time, I think. But we're actually co-authors, I think, on the waste divide paper.
Mhm. Yep.
These crazy kind of connections. But I
Yeah.
wanted to see, you mentioned Thwaites in the context of 1 to 3 meters worth of ice. And then you also mentioned, potentially doing field work there. But could you just weigh in on what you think about the projections for when that ice might come out? Because they're pretty dire. I mean,
Yeah.
3 meters of ice itself is really dire, right? And so what do you think about those predictions? And what are the uncertainties? What more do we need to know to make them better, and so on and so forth?
Yeah, that's a great question. So yeah, I was using rough numbers there, 1 to 3 meters. And the fundamental situation at Thwaites Glacier is sort of a classic arrangement in glaciology. It's been recognized since the late 60s as marine ice sheet instability and the importance of how ice shelves hold back the ice upstream. They buttress, or they're sort of the cork in the bottle. And if a stable frontal position of an outlet glacier moves back to where the bedrock continues to deepen, like in West Antarctica, can just run away. So yeah, the big question, how much, how fast? I can't remember exactly the latest, in the latest IPCC report, the current number for coming from Antarctica by the end of the century. I think it's on order of just 10 centimeters from Antarctica alone, which is quite a bit from just one place. And that would almost all be from Thwaites Glacier. So, that's a relatively small amount. Mountain glaciers in Greenland are still the first players, the first to go, and are rapidly contributing to sea level rise. I think the scarier thing for me, I guess maybe as geologists, we're more tuned to care about a slightly longer time scale. But if you looked at the projections out to 2300, the error bars on Antarctica's contribution get to be several meters, like more than 3 meters. And that's just a massive uncertainty. And if those upper end numbers are right, that's a massive thing for society to adapt to, even on those long timescales. So I feel like that's a struggle I don't know if it's the most important thing to communicate to people at this time, but we're very much committed to long-term change from melting ice. And I always find it fascinating too, that because where we're losing the ice is so focused in space, right? We're going to lose tons upon gigatons of ice from Thwaites Glacier, and that actually changes the gravitational pull of that concentrated mass in Antarctica. So that also has an additional effect of Antarctica's letting go some of its gravitational attraction, which actually makes sea level rise, for us, furthest from Antarctica, a little bit greater because of the gravitational effect as well. Yeah, it's sort of interesting to have so much of that concern about sea level rise focused on one glacier system. I mean, it's a big system, but for it to be in the most inconvenient place is sort of obnoxious as well. So I think that's a long-term struggle for the National Science Foundation and the Antarctic program. Is we need to be monitoring and understanding that whole coastline, but particularly Thwaites Glacier, in perpetuity. We're never going to fully know what's going on there. We always need to be refining what we know. So yeah, it's tricky. The logistics are really the primary logistical constraint for doing that work is fuel for the large C-130s that fly out there. And so I think there's going to be a shift too to keep supporting this research, to establish basically an overland road, a traverse route from McMurdo Station, which is on the other side of the continent from Thwaites. But yeah, it's a tricky place and a really big object where we have to understand the top of it, the bottom of it, under 2 miles of ice. You need to understand 200 years of climate that's been building up to this moment. Yeah, it's complicated.
So, I mean, correct me if I'm wrong, but the IPCC report does that differ from the DeCanto and Pollard projections? I mean, I think there's been a general, I mean, a lot of people think that, you know, I'm sounding like Trump. Many people think, but that the IPCC sea level estimates, you know, tend to be on the low side.
Yeah, and they sort of give themselves a get out of jail free card by saying, but there's a non-zero chance of this really catastrophic outcome. I can't remember how it's summarized in the summary documents, but yeah, I mean, it's certainly more conservative than DeCanto and Pollard, and those numbers are treated in mixed ways in our community as well. That model is still a little bit toyish, especially when they added this new mechanism of ice cliff instability, some critical height of an ice front where it was just going to catastrophic, like sort of collapse like a deck of cards.
Mhm.
The how real those mechanisms are is still under debate. So, you know, they're the high end projections for sure, and I think they would admit that. But yeah, you need that full range of perspectives, and there are a lot of people who are trying to refine that understanding. But it certainly will be a consequence. You know, for one glacier to be so consequential for so long, it's pretty remarkable.
Mhm. Well, thanks.
Yeah, thank you. Let's see. I see a few more questions, but I don't know how long you want to go.
I wonder if the people who put the last few questions in the chat are here and could chat with you outside, or are they remote? Max, are you here? No, Max isn't here. You're across the
I'm
Very
a
much
long way
not.
away.
Yeah.
Yeah.
Yeah, maybe answer that one.
Yeah, you know, so Max asked if we know. I know the current uncertainty in snowfall along the West Antarctic coast. And I don't know the number. It's on the order. I would, you know, imagine it's around 10% or less. But the largest uncertainty in snowfall estimates, I guess you would call them, because they're not an observed variable in climate reanalysis. They're forecasted from other variables, and they are most uncertain along the coasts. And you know, the coasts are a relatively small fraction of all of Antarctica. It's actually more, you know, most important that we get the millions of miles of East Antarctica right, because even small errors in snowfall there add up to gigatons upon gigatons of errors. But along the coast is where the ice shelves are, and the ice shelves are the critical corks in the bottle for the ice sheet. So if you're getting fundamental things like snowfall wrong for ice shelves as you're modeling their their future, their demise, however you want to say it, it is a really important term, and it's especially important because snow is a really complex material, and if you know, our best way of observing it is with a satellite platform like ICESat-2, which is basically a LiDAR in space. You know, it's a green laser, so it shouldn't penetrate that deep into the snow, but you have a snowpack, which is then, as soon as it falls, it's slowly starting to compress. And so that compaction and the fernification process, we call it, I mean, their entire good friends of mine are like NASA's specialist on Antarctic fern, because it's such a huge uncertainty how, you know, as soon as the snow falls, it's not done changing. It's immediately going to start compressing and metamorphosing, and that transition from snow to ice. So yeah, it's a complex place, and we have to, so those really small physical processes, like how a snowflake turns into an ice grain, really matter when it's, you know, trillions of those snow grains all over the continent, and we're just, you know, we need to get numbers as correct as possible. Looks like one more question here. Who determines priorities on what research projects related to climate change get funded? Isn't it a priority of Antarctic research? So it's absolutely a priority of Antarctic research, and the document that the NSF for Antarctic and Southern Ocean research that they go to right now is a 2015 report from the National Academy of Sciences, which is basically the only body that can advise NSF. We just went through this with our workshop with them. You know, scientists don't advise the NSF. We can make recommendations and voice the needs of the community. But that document, which was put together by a panel of scientists, identified the changing Antarctic ice sheets as the highest priority science topic for the National Science Foundation across all Antarctic science disciplines. So the top one was changing Antarctic ice sheets, and it was understanding Antarctic ecosystems in a changing world, and then it was understanding the birth of the universe or something like that with the telescope and other observational platforms at South Pole. So expert panels that advise the National Science Foundation, I guess, set the priorities. And then our program officers determine who of us, after review processes, are lucky enough to keep doing the work. So it's quite a complex system. It's your quick answer, though.
Okay, let's thank Peter again for his talk.
Thanks. The Zoom claps.
Yeah.
Thanks so much for inviting me. It's really great. I feel like it's part of quasi coming out of our COVID caves here, although we've got to be careful still.
Right. Well, I hope anyone around will converge outside just to have some in-person interaction. We'll see you soon.
Thanks. Hope to see you.